So in the notes last time we saw, here's the length. It was, I think, the length and the weight of different fish in the ocean. And so we practiced last time with like cube root or cubing. Your homework involved squaring or taking the square root. And so today the transformations that take place are logarithms. And remember, you won't be having to make a decision to take a logarithm. It'll be stated for you that that's what was done. So it says, here's what happened when we take the base 10 logarithm. That's called common log. So if they call it common log, no, it's log base 10. Or if you just see the word log, it's log base 10. Well, it says what we decided to do is we decided to take the log of both variables, the length and the weight of these fish. You can see that over here in the graph. The word log is in front of length, explanatory variable, and it's in front of weight, the response variable. You can also see it in the title of the computer readout. So it will be obvious to you what was done. So what we're going to practice again is taking this computer readout and writing the equation for the least squares regression line so that we can make a prediction about the response variable weight when the length is 36. So here's really what is going on. We took the log of the weight, we want to be able to predict the weight. Over here is just kind of think of it, the skeleton is a plus bx. So just like always, look at your computer readout. What do you see the y-intercept is? You know where to spot it? Out of all of these numbers, what's the y-intercept? What's the a value? You guys are really quiet today. It's always next to the word constant. So it's that negative 1.89940. Let's avoid rounding until the very, very end. There's the y-intercept. And then it's plus if your slope is positive. It's minus if your slope is negative. And the slope can always be found right underneath the y-intercept. And in this case, it's 3.04942. But I don't get to just stick an x on there because the logarithm was taken of the x values. And instead of x, let's put log of length. I'm going to erase my x and put length so we've got the words there to back up what we're doing. Don't let the log stuff scare you away. All we're going to do is take this equation where the log was taken of both variables, and we're going to plug in 36 for the length, and we're going to see what we would predict for the weight. So log of the predicted weight is going to equal negative 1.89940 plus 3.04942 times the log of 36. There are no variables over here on the right-hand side of the equation. That means all you have to do is type this crazy looking expression into your calculator and it will tell you the value of all of that stuff. So let me do this with you because I'm not really sure what's going to happen on these TI-84s. Let's do negative 1.89940 plus 3.04942 times the log of 36. So all that craziness over there shrinks down to 2.846. Yes, ma'am.
Thank you.
Huh? All right. Now, think about the few things that I put up on the screen for you this morning just to kind of recap logarithms, okay? Now, over here, I don't know what the predicted weight is. I don't know what y hat is. But I do know the base of the log is 10, and I do know that the entire point of logarithms in the math world is to get the exponent alone. So if I change this from a logarithmic equation to an exponential equation, then I'll have the predicted weight. The base of the log is the base of the exponent. The number by itself is the exponent. And maybe that'll help you remember how to rearrange these. So now, the left-hand side, there aren't any variables there. That's something we can just pick up our calculator and type in, and we'll have the predicted weight of a fish when the length of the fish is 36. So 10 to the power of 2.846, or if you want to be super duper accurate, 10 to the power of, and then you can just go up and highlight that long decimal and hit enter, and it will copy and paste it down for you. That way you're not rounding until the very, very end, and you can see the discrepancy here. I think an AP grader would be a-okay with you showing how you rounded it and justifying your answer was 701.46. But if we're being really accurate, the predicted weight would be 702.13 grams. That's the only example you're going to see in the notes of me working a problem where the log was taken of both variables. Okay? Now, this is a completely different problem. We're not talking about fish anymore, so this is almost like a start from scratch, okay? The number of transistors on Intel microprocessors has been growing exponentially since 1970. So look at the scatter plot and you can see that there's like this exponential growth. Well, statisticians don't like data that's curved, so we're going to force it, we're going to straighten it out so that we can use a line, a least squares regression line, to predict. And it says the second scatter plot shows the result of using the natural logarithm, ln, to transform the number of transistors. Well, you can just look over here, and you can see ln, the natural log was taken of the response variable, but we didn't mess with the years. It doesn't say ln or log or anything like that over it, okay? State the equation of the least squares regression line. Predict the number of transistors in 2020. Okay. So the natural log was taken of the number of transistors. And I want to be able to predict the number of transistors. It's the response variable. The computer readout tells me that the y-intercept is 7.2272. The slope is positive, and nothing was done to the years since 1970, so the slope is 0.3542. And my x value is years since 1970. Predict the number of transistors in 2020. Does that mean we're going to plug in 2020? No. How many years since 1970 is the year 2020? Golly, that makes me feel old. Yes. 50 years since 1970. I always think of 1970 as 30 years ago. All right, 50. You don't have any variables over here, so pick up your calculator and figure out the right-hand side. .2272 0.3542 times 50 years since 1970. 24.9372. And the reason I started class the way I did today is because I want you to understand again that natural log, that's the same thing as log base E. Log base E. Make a little note to yourself. So I'm going to be very repetitive here. The whole entire point of logarithms is to get the exponent alone. The base of the log is E. So E is the base of the exponent. The exponent is the 24.9372. If you use your calculator to find that, you'll be able to predict the number of transistors in the year 2020. So you have to hit second divide to get your E and raise it to the power of 24.9372. I feel like I did something wrong. No, didn't. I think I just wrote down the wrong answer in the notes on Schoology. Is this what you're thinking? Can you verify that? Okay. So I think I made the classic mistake of not reading the entire answer, and I put like 6.76. What does all this E business on the end mean? Yeah, it's scientific notation. It's the way the TI-84 tells you times 10 to the 10th power. So here is really our answer. It would be like 6.76 times 10 to the 10th. That's the prediction. We're going to get a really, really big answer, you guys, because this is an exponential growth. And if you move your decimal over 10 times, I think you're in the billions. I don't know, I'd have to actually write it out with all the commas and everything like that, but this would be good enough. So that's the predicted number of transistors. Okay. If you're given several different ways to model the relationship between X and Y, how do you know which is best? And you are going to choose the option that has the most random residual plot. Choose the model with the most random residual plot. If for any reason you see two different options that look pretty random and you're still not sure which one is best, then you can look at R squared to break the tie. R squared will break the tie of two random residual plots. But that's a pretty rare thing that you even have to default to. Most of the AP questions I've seen, it's pretty obvious which of the answer choices has the most random residual plot. Do you have to be able to create a model? Like, do you have to be able to make the decision of taking a logarithm? No. So it will be told to you the transformation was done. You don't have to make that decision. Now go to the back. As part of the American Presidency Project, the annual State of the Union address has been analyzed going back to the first president. It turns out that the president's use of the word America has increased in relative frequency or percentage over the years. Here's a linear regression output for 3 different models, along with a residual plot for each model. Model 1 is based on the original data. if I'm looking at Model 1, let's just take a glance at it. The percent of times the president uses the word America in his State of the Union address versus the president's number, like the 45th president, that would be what it's saying when it says president number. I'm looking and the residual plot shows a pattern, which means the data is not going to be linear. The R-squared value is pretty weak, and so forth, okay? That's Model 1. That's the original data. Well, because it wasn't linear, Model 2 and 3 involve transformations. So let's look at Model 2. Look at the residual plot. Does it look scattered, or do you see a curved pattern there? And you just have to kind of get used to the way these might look. It might, at first glance, look scattered. But compare it to Model 3. Which one is more scattered? 2 or 3? 3. This one actually kind of has this curved pattern to it. That's not good. And look over here. When I took the log of both sides, it didn't straighten my data out. The residual plot is showing. But Model 3, when I just took the log of the percentage of times the president says the word America, the residual plot is showing complete scatter. So that's going to be the best model. So part A says, which model does the best job of summarizing the relationship between the president number and percent America? Explain your reasoning. Model 3 does the best job of summarizing the relationship, that can be a sentence. We probably need to say the residual plot for Model 3 is the most random. Or is the most scattered. And let's go ahead and just make a note right here. Look at the R-squared value. It's a lot stronger than Model 2 was. It's a lot stronger than Model 1. So let's just put and the R-squared value is largest for Model 3. So I'm letting the AP grader know that I looked over here and I can back it up with the residual plot and the fact that R squared is large. We want our R squared to be large. Bigger R squared means bigger R value, shows more strength and correlation. That's pretty much it for A. And then we're going to just use the model chosen. So we're going to use Model 3 and calculate and interpret the residual for the 45th president whose State of the Union address contained 1.3% American. So look back at Model 3, use the computer readout, use the fact that the log was taken of the percent America. On Model 3, the y-intercept is negative 1.4325. The slope is 0.0315 times the president number. Wants us to make, calculate and interpret the residual. So what I'm doing right now is I'm going to find the predicted number of times the 45th president says the word America. So I'm going to plug in 45 for president number. So grab your calculator. Negative 1.4325 plus 0.0315 times 45th president. We still have to evaluate the percentage itself, so take it from logarithmic, swap it over into exponential, log base 10 to the negative 0.015 power will give me the predicted percentage of times the 45th president said the word America in his State of the Union address. But that's not answering the question, so we're not quite done. It said to calculate the residual. Calculate and interpret the residual. Here's what I predict as the percentage of times he says the word. Turns out, the percentage of times he says the word America is 1.73. How do you figure out residuals again? Actual minus predicted. Well, the actual percentage is 1.73. The predicted is 0.97. So subtract those, and the residual is positive 0.76. The interpret piece is going to be, he used the word America about 0.76% of the time more than predicted by the model. He used the word America about 0.76% more than predicted by the model. So that involved more work than you might have initially thought. But that's it.